Hi there. Now for this question we're given this uniform rod AB of mass m and length 2a, and it's freely hinged at this point A, and a particle of mass m is attached to the rod at B, and the rod is held in equilibrium at an angle of theta to the horizontal by a force of magnitude F acting at this point C, where AC equals B. Now the force F at C acts at right angles to the rod AB and is in the vertical plane containing AB. And what we've got to do is show that F equals 3amg times cos theta, all divided by B, for 4 marks. So if you'd like to have a go at this, just give you a moment then to pause the video, and when you come back you can check your work solution against mine. Okay, welcome back then if you had a go. Well, let's just first of all put the forces that are acting on this uniform rod AB. Now it's of mass m and length 2a, so therefore the weight is going to act in the middle because it's a uniform rod, so we'll just put the weight down there, mg newtons then. We're also told that a particle of mass m is attached at B, so therefore there's going to be the weight of that particle acting downwards, mg newtons. And because A is fixed here at some point, then there's going to be some kind of reaction force coming off the hinge, if you like, here. And so what I'm going to do is split that into 2 components. We'll just say we've got one component that way, we'll call it x newtons, and we've got, say, another component going upwards, we'll call it y newtons. It doesn't matter if you put y going down or even x going the other way, the mathematics will sort itself out, but I feel that x has got to go in this direction anyway, because the rod will be pushing against the wall. Not sure what's going to happen about y, so it doesn't really matter, as I say, whether you go up or down. Now it's because we don't know the forces x or y at this point A that this means that the best thing we could do is to take moments about the point A. And if we're going to take moments about the point A, we need to think about these 2 forces here, which aren't perpendicular to the rod, to think about splitting them into components. So what I'm going to do is just put a dotted line in here perpendicular to the rod. And that would mean that the angle in here is going to be theta, same as the angle here. Okay? Now, if we take moments then about A, just put this here, moments about A, we need a positive sense. It doesn't matter which way we go. I'm going to take anti-clockwise as positive. So therefore, I've got all of F acting perpendicular to the rod, so its moment is going to be the force F multiplied by the distance B. So we're going to have FB. And then if I look at the moment of the rod given by the weight of the rod, then the weight can be split into 2 components, one down the rod and one perpendicular to the rod. We're not interested in the one down the rod because it passes through A. The perpendicular force will be mg cos theta, so we've got mg cos theta, and that will be multiplied by the distance from here to back to A, where it's a uniform rod of length 2a, so this distance must be A, so we'll times that by A. And this wants to act in a clockwise sense, so it's going to be negative there. Okay? The same is going to apply with the particle of mass m attached at B. It wants to turn the rod in a clockwise sense, so its moment is going to be minus, and it's going to be mg cos theta, that would be the component perpendicular to the rod, mg cos theta, but this time it's multiplied by the distance from B to A, which is 2a. So we'll times that by 2a. And this is our resultant moment, and it equals 0 because it's in equilibrium. So what have we got? We got FB, and we've got minus mga cos theta, and we've got minus 2mga cos theta. So that's going to be minus 3mga cos theta, and that's going to equal 0. So just rearranging this, adding 3mga cos theta to both sides and dividing by b gives us f equals 3a mg cos theta, all divided by b, which is what we had to show. Okay?